All right, thank you to those who have voted in our most recent poll, and that said, there has been a really noticeable drop in how many people participate in these community posts. I highly encourage it, and hopefully Bob, by answering to your request, that will encourage more of you to engage in those. So as you saw from the poll in the beginning, all three of you voted to have a tutorial on rotating complex equations. Well, okay, go back a little bit. Graphs with multiple equations, because complex equations have a different meaning than difficult. So that said, the link to this graph that I'm looking at right now is available in the description. There you will find examples of shapes that are made of more than one equation. Other thing is you can follow along here if you want. What I'm going to do just to make this explanation easier is to start in an empty graph, explain the rotation process, and then we'll translate it to this larger example that I'm looking at here. So I would open up a new graph here. You are highly encouraged to follow along, whether it's on a blank graph or on the example graph they open in a new tab. So for this example, I'm going to start with the ever popular parabola here, and the method that I'm going to introduce, it's not something that I can explain very well, and for that reason, I'm going to include a link to another video. It explains this much better than I would have been able to, and so I highly recommend checking it out. It'll make this whole process make a lot more sense, certainly better than going through. It'll make this mechanical process more meaningful. Alright, so to make this process easier, we're going to convert this into a parametric equation. So parametric equations are equations that introduce a third parameter, the parametric. We call it t for time, and the way it would be formatted here would be we set the x to be just a plain t, and what that means is if x is t, then this y must be a t squared. So because x is just simply t, the range of values that we define here is going to be the same range as what this x is going to be. And so if we made this run from minus, okay, you can't see that, minus 4, can't see that either, minus 2 to 2, you can see that this blue line here encompasses this x to be minus 2, and this is the upper bound here to be positive 2 here. And the second thing that I recommend doing is alright, I'll recommend it shortly afterwards, because it'll give you that foresight needed to see why we're making the decisions that we are right now. Alright, so now if we want to rotate this, the idea here is, so I want to apply the formula here. Again, really recommend that they check out that other video to understand why. Alright, so we're using trig functions. And so let's define a degree variable. So this has to be in radians. And I'm going to do 30 degrees, and that's pi over 6. And this derivation actually comes from the idea of a circle having 1 unit in radius, and therefore if we make one full revolution around, that'll be the circumference of it, which is 2 times pi, and so if you want 30 degrees of it, we apply that at 2 pi out of 360 60-degree rotation, and that's where this number comes from. And Desmos has reserved theta as is for polar equations, if I remember correctly. So that variable is so that name was reserved. So that's why I took the liberty to call it D instead. All right. So it's t. So it's t cosine of the angle in radians minus our function t squared times sine of our angle, and then this would be t sine of the angle plus t squared times the cosine of that angle. And you can see now this rotation is you can see this rotation happening here. And this should allow us to add a slider here. So if I make this 0, it should offer us to have a slider. It doesn't. Let's try that again. There we go. So you have to throw in a value that doesn't recognize. Only then it'll make a slider. So if you slowly move this value around, you can see that you can see that we have this parabola rotating. You can see that at our original t range -2 to 2, this is the bonus here. It's not being you're not seeing this being chopped off at this 2 here. It's actually respecting. It's actually respecting our rotations here. All right, so that's the idea here, and so if you're thinking ahead here and thinking, okay, well, what if we have long equations? What if, would that not make this process as super painful? And you would be right about that. And that was why I took a step back and said, well, let's go through this tedious motion first so that we can see a justification why now I'm here going to make the recommendation for setting f of t to be whatever function you have. So this is on the assumption that suppose this is some really long equation. So assume this for now that a parabola is, quote, difficult. I'll turn it off just so it's not distracting. And also now, what we should be able to do is if I wrote f of t in here instead of t squared, you see that this is still working the same way. Now is suppose now we have this ridiculous complex equation plus log squared. All right. We get the point. So we rotate this back to 0. So as you can see here, that's you can make your equation as ridiculous as you want, and yet the complexity of this form right here still stays the same. So you don't have to see this giant monster just jammed right in here. So that's the idea of it. And now we're gonna move back to our larger example here and see how we can deal with not just having multiple equations defining a shape, but also dealing with these translations that have happened. Here, I'll demonstrate shortly. All right, we'll start with this letter A here, and this A is okay. We're looking at this upside down parabola here. So that's what this equation is highlighting. Now, if you made it up to this point, right, you may be inclined to say, well, let's make a function f of t. So I was like, okay, so we're going to, everywhere we see an x, we're going to replace it with a t. And minus t plus 6 squared plus 5, and what that means is that, all right, let's define another one here, that our parametric function would look like, I'm just going to copy this formula straight over here. Call it angle, I want to subscript it A. In fact, just so that we do have a slider defined, we want Desmos, if we could have this do the work for us, why not? Let's do that. What I'm doing here is getting this set up to what we had in our example graph here. So that's why I'm moving somewhat quickly here, is so that you don't have to sit through much of this setup process. And this is not F, we're calling this F1. And the reason for its labeling is so that if you have 100 functions, and you say, okay, yeah, first function I'm going to call it F, second function I'm going to call it G. I don't want you to run out of letters and get stuck with having to come up with some word creative tricks to get around it. So that's why the subscript here, it removes that worry. All right, and then a T range would be the same as what you see up here. All right, well that's great. So that means if we rotate this around, we should have absolutely no problems, right? And what do you notice about the rotation? It's rotating around what? correct answer is the origin. Now, unless that's what you want, you can carry on. What I recommend is to take advantage of a parent function. What am I talking about? So this function came from somewhere, right? Like it's there. Underneath this entire shebang is really just is none but a t squared, and I'm gonna do something here. This spans 4 units in length, and so this parabola is now going to be placed here, right at the origin. So we want this to be 4 units in length. We want this to be 2 units to the left and 2 units to the right, and that's going to center it right here. Now, how do we get it back to where it was before? Well, before we do that, first I want to demonstrate that this parabola is now rotating with its vertex here as the axis of rotation. So if we now apply the transformations and say, okay, well this is saying move to the left by 6 units. Okay, so we go inside this function here, go inside this x parameter here. I'm going to move 6 units to the left. We also want to move 5 units up. And rotate it, well, not rotate it, reflect it across the horizontal axis. Yeah, so this is applying to just the x only. This isn't to the negative y. So I believe the way to go about that. So we actually shouldn't have added the 5 first. We instead should have reflected it first. Let's put parentheses around here, make it negative, so now that's reflected, and then we're going to move the 5 units up. And so now if we make this 0, you can see that we now got our original equation back. If that did not at all make sense, or if there's anything about that did not make sense, absolutely leave a comment down below. So what can we demonstrate now? Well, we can now demonstrate that this parabola here rotates along its vertex. The other question now is, how do we get it to rotate along this point here? It's minus 6, 3. That's where the center is. Well, in that case, we want to define a function. We want to have a different parent function, because right now, if we had the function parented at t squared, if we had t squared as a parent, its axis of rotation is going to be along where its origin was, which is that point here, where my cursor is at, minus 6, 5. That's where it's going to be rotating around. So how do we get it to rotate around here? Well, this is 2 below this one. So if we move this to below, and rather than adding 5, we now add 3. Now this should be rotating along that center. Did that make sense? All right. So I'm pausing momentarily to give you a chance to pause the video if you do need to head down and to ask any questions. On the next piece that I'm moving on to is this line here. So this horizontal line is going to be interesting because as if you look at the original equation here, actually I'm going to go ahead and delete that because we're not using that anymore. This one is still relevant. Well, this one is a constant straight line, and it doesn't really make sense to apply any to throw these transformations at it directly. So what I'm suggesting is we do go for the parent function. So the parent function I'm recommending is f2 of t is equal to t, because this line is rotated, and you can treat this as a line rotated 45 degrees. So if you kick this off with the 45-degree rotation right out the gates, well, I'll show you what I'm talking about here. Hey, what does this f of t translate to? In fact, perhaps for this case, we don't even need to do this since it's really is writing y equals x. Alright, so let's make it just so you can see this from -2 to 2, and these other ones here are just straight up distracting. Let's okay. This one's gonna stay here. So if we add a 45-degree, actually, we want this to be horizontal, so we want to rotate this back down by 45 degrees. And so convention is that clockwise is negative and counterclockwise is positive. So in that case, we really should be subtracting. So if this much is pi, this is pi over 2. This is then that must mean we should be subtracting pi over 4. Am I about to get this wrong? That's what it's about to look like. Minus pi over 4. All right. So I did get the convention right. And so this one, so this line here is already has this 0, 0 as the axis of origin here. And so this is where we go back in and apply our boundaries here. That's why we need to do a bit of math. So we need to find out what is the length of this. Alright, so the way you find out how long this should be, it should be be its length divided by 2, so it would be, in fact, just wanted to use, this is a calculator. Why not use it? Minus 4.586 is 2.828. That's actually a very easy number to work with. Okay, 1.414. That number looks really familiar. When I'm thinking about that, it's looking like the square root of 2. .414. This is 1.414. Okay, and where's it centered? This is centered at so we're gonna move left. We're gonna move left 6, and then we're gonna move up 5. No, 3. Why is this not working out? Did I mess up somewhere in the math? Length looks alright. Right, that's odd. I estimate this at I just did estimate at -1 to +1 here. And so now if we apply the rotation, would you look at that? Well, that's funny. Well, that means we need to flip the. We need to change how this line rotates, because while this is interesting enough, a red line is rotating by convention. Is if you see, if we move negative, the red line moves clockwise as it should. On the other hand, the blue line doesn't. So let's give that a fix. All right, so turns out that the way to do it was to make all the x values negative except for the translation here. So we'll take the minus of the formula and then followed by the left translation here. Now if you rotate your if you move your slider here, you see that that your shape is rotating along the right origin. So yeah, I do realize this video is getting long, and again, if any of this doesn't make sense, and any clarifications, do not hesitate to ask in the comments. Thanks for making it this far, and I'll see you in the next video.